visiting amarpathshala.com. This is part 2 of the chapter Chemical Bonds and the Structures of Substances. And we start today's lecture by discussing the topic boiling point. Now, what is a boiling point of a substance? A boiling point of a substance is a temperature at which the particles of the substances are moving at such a speed that on its surface you can see the surface boiling. Why does that happen? We know that every matter is made up of molecules and that those molecules are always vibrating. Now, if you increase that inherent vibration of those molecules, they often tend to move at much higher speeds, and on the surface those high-speed movement can sometimes at very high temperature cause formation of boils, and thus comes the term boiling point. A boiling point of a compound will depend on the temperature at which this compound will boil will depend on the kind of bond that compound is made up of. For example, in here you can see a scale. The scale has a temperature marked by degrees Celsius, and in here you can see some numbers. It starts with a negative 250 degrees Celsius, and then you see 0 to 50, 500 and upwards. On the other side of this scale, you can see some dark dots and the name of some chemicals, and on top you can see some lighter dots and the name of a few other chemicals. If I have to break down this scale to you, this scale is a demonstration of substances, elements or compounds whose boiling temperature varies due to the bonds that they are made up of. For example, in case of water, it is a simple substance with weak bonds. The bonds are not that strong, therefore its boiling point is somewhere around 0 to 250. And as we know, the boiling point of water is 100 degrees Celsius. Same with ethanoic acid, hydrogen chloride, nitrogen, helium, ethanol, etc. All these substances, they are lower on the scale of boiling points. Why is that? It's because of their bonding. The bonding between the atoms are weak compared to those on above, as a result of which they range below on the scale. And when you go up, they have a bond that is much stronger. Barium oxide, silicon dioxide, aluminum oxide, calcium fluoride, calcium oxide, etc. Their bonds are so strong that in order for them to actually melt and then boil, they often reach temperature as high as 3000 degrees Celsius, which is pretty high if you think about it. So, when we are looking at the boiling point or the melting point of a substance, we can discern a couple of things. One, what kind of substance they are. If they are substances which are molecular or which has weak bonds, then they will most definitely have melting or boiling points which are lower on the scale. Thus, we get an idea of their bonding. And when we see substances that have significantly higher melting or boiling temperatures, we can say that either they are large molecules, or even if they're smaller molecules, their bondings are so strong. And this is a key point, because this strong bonding is usually because of ionic bond. Ionic bond is a type of bonding that we have discussed on part 1 of this lecture. And ionic bonds allows these molecules allows these compounds, not molecules, compounds to have such a high temperature that, being simple, they usually melt under temperatures such as 3000, 2500, etc. Either this, or they would be molecules with a structure that are giant, and those molecules are known as giant or macromolecular substances. And third, if they're not ionic bonded compounds nor macromolecular substances, they would be metals. Now, metals are elements, as we have said over and over in many lectures. Metals are elements that are usually found on the far left side of the periodic table. Metals do not have a giant structure, yet they tend to have boiling points or melting points that are extremely high. Why? That is something that we will discuss in this lecture at the part metallic bonding. In order to understand the bonding of a substance, we classify them according to their boiling point and another characteristic, which is their electrical conductivity. The boiling point tells us what kind of a substance they may be. For example, if they have a low boiling point, they are molecular substances. If they have a high boiling point, they are either ionic or macromolecular or metallic. But when it comes to electrical conductivity, along with boiling point, it also gives us a better idea about the bonding between the substances. For example, if you looked in this table right here, you can see that this column shows the boiling point. The substances with low boiling point, whose boiling points are somewhere around 20 degrees or lower, their electrical conductivity is none. They do not conduct electricity at all. And their bonding can be therefore classified as molecular. See, what happens is that when you have substances with such low boiling points, you can automatically assume that the molecules forming them, the molecules that they are formed of, are very low in number. So you can say that they are either gases, like carbon dioxide or steam or oxygen, or they are simple molecules like water, etc. So in case of electrical conductivity, you need particles that can move and therefore carry electrical energy, but their particles are so less in number and they have such huge space between them that electrical conductivity becomes an impossibility. And with that character, you can automatically say that their bonding is molecular. Now, the problem arises when we reach, or when we are when we are handling molecules that are higher on the boiling point range. For example, the ones that has a boiling point well above 900 degrees Celsius, they can either, their electrical conductivity and their characteristics in electrical conductivity will say volumes about the bond that they are made up of. For example, ionic bonded materials, ionic bonded compounds will conduct electricity only when they are liquid. Either they have to be molten or they have to be dissolved in a liquid where they are soluble. And this is the only way in which ionic solids will conduct electricity. In case of metals with metallic bonding, they will conduct electricity when solid or liquid. The reason behind this is hidden inside their bonding. And in case of macromolecular solids, even though they have a very high temperature, they do not conduct electricity at all. So if I handed you a substance A and I did not name it, and I provided you with the information that it has a boiling point of, say, 25 or 50 degrees Celsius, and it does not conduct electricity, then you can safely say that it is a substance that has simple molecular bonding. How did I reach to that conclusion? First, I investigated its boiling temperature, which was low, and then I noticed if it conducts electricity or not, which it doesn't. So the only option is molecular. But if substance A had a very high boiling temperature, say if it was somewhere around 750 or such and such, but it still did not conduct electricity, then you could have said that the substance A was a macromolecular substance. But if it was something that had a high boiling temperature with a high boiling temperature and it conducted electricity in a solid or liquid state, it would have been metallic. And if it conducted electricity only when it was in a liquid state, it would have been ionic. So these are basically the two parameters with which we can identify substances or into which type of bonding they belong to. The boiling point and electrical conductivity. Guys, so far we have discussed the parameters which differentiates substances into their bonding. Now let's discuss the substances. Molecular substances. The name defines the type of material it is. Molecular substances are compounds or molecules that are made materials that are made up of simple molecules. For example, carbon dioxide. Carbon dioxide is a gas molecule that is made up of C and 2O. The bonding between C and O are this bonding between carbon atom and an oxygen atom is what is known as intermolecular bonding. In case of molecular substances, this intermolecular bonding happens to be weak, which is why they have such low boiling temperatures. And this weak intermolecular bonding also means that their structure can be destructed, or their structure can be changed easily, much more easily than the other substances that have ionic bonds or metallic bonds. Molecular substances tends to have smaller structures. They are simple. They are usually gases or liquids, etc. They are not complicated. And molecular substances are made up of elements that are not metallic. For example, molecular substances are usually made up of non-metallic substances. As you can see, in case of carbon dioxide, this is one case. In case of other non-metallic substances, such as in group 7, in that whole column, in that whole group, the entirety of it is non-metal. Chlorine, fluorine, bromine, etc. All of them have a diatomic stage. They exist as two atoms that are bonded with each other, forming a molecule of chlorine gas, fluorine, bromine. In chlorine's case, it is a simple greenish yellow gas. In bromine, it is a reddish brown liquid. In case of iodine, it exists as a ash gray, ash black solid, which also forms a deep purple vapor when you heat it. Even in those cases, they are made up of simple molecules, two atoms bonded by covalent bonds. So simple molecular substances or molecular substances are materials that are made up of atoms that are bonded by weak intermolecular forces. Intermolecular forces. And these forces of attraction between the two atoms of the molecules happens to be weak. Thus, these molecules have lower boiling temperatures and zero electrical conductivity. Now let's discuss ionic bonded molecules. So ionic substances. In part 1, we discussed what an ionic bond is. To repeat myself, an ionic bond is a bond between two ions. An ion is a structure that forms when an atom has an excess or a depletion of electron. Excuse me. When an atom has more electron than proton, it forms a negative ion, and when an atom has more proton than electron, it forms a positive ion. An ionic bond usually forms between the electrostatic attraction between a positive ion and a negative ion. So when we have that bond, what we have is an ionic substance. The most common ionic substances that we know of and use every day is common salt, that we use it everywhere in our foods, in everything. Now, common salt has a common salt is a chemical compound with the name of sodium chloride with the chemical formula NaCl. What you see in front of you is a simple diagrammatic representation of a sodium chloride crystal. The bonds between these right here, this is what an ionic structure and ionic bonds look like in sodium chloride. As you can see, in here, this is the key of the ion's position inside the bond. Now let's return to the bond. In a sodium chloride crystal, the crystal has a lattice structure. Lattice, the word lattice means a structure that is a very regular maze. And in here, you can see that each sodium ion is bonded with another chloride ion, which is bonded with yet another sodium ion, and all this is forming a complicated 3D lattice structure of crystal. And this is one crystal, guys. The salt that you eat, the salt that we put in our food, or the salt that we use, is made up of millions of such crystals, and each singular tiny crystal particle has this complicated of a bond structure. So you see, this structure, which is so compact, which is so regular, and is so beautifully attached in such meticulous manner with each other, each plate, each ion strongly bonded with the another. This gives the sodium chloride molecule a compact structure and a very, very high melting point. A melting point that is well above thousands. And this is the same with each and every ionic substances. Take magnesium oxide, for example. Magnesium oxide is also an ionic substance which has very high boiling temperature. Now, apart from high boiling temperature, what ionic substances also have is electrical conductivity. What we have discussed in our electrical conductivity parameter at the beginning of the lecture is that in case of ionic substances, they only conduct when they are molten or when they are dissolved in liquid. Why does that happen? See, in order to conduct electricity, you need agents that can carry the electrical energy forward. In case of these substances, it is these ions. Now, in the structure, when they are compact, when they are solid, that is, these ions are not free, and as a result, they cannot conduct. When they are molten or they are dissolved in a liquid, these bonds are broken, and therefore the free ions are able to conduct electricity throughout the liquid that they are dissolved or molten into at that point. The melting point of ionic substances depends on the strength of their bond. The bond strength depends on the charges that are involved. For example, the higher the positive and the higher the negative, the stronger the charge. Or the smaller the positive and the smaller the negative, the stronger the bond. These two statements are contradictory, but they make sense. Let me tell you how. See, in case of sodium chloride, sodium forms a positively charged sodium ion, chlorine forms a negatively formed chloride ion. Sodium ion and chloride ion both have single positive and single negative charge distributions, and their sizes are almost the same as well. Therefore, the ionic bond that forms between them tends to be very strong. But in case of an ionic substance that wherein the positive charge is bigger than the negative charge, that bonding between them will not be as strong. For example, calcium chloride, CaCl2. Calcium ion has a double positive charge, so we can assume that it is a big ion. But compared to that of a chloride ion, the bonding that we have seen in sodium chloride will be more stronger than here because of because in here the ion distribution, the charge distribution is much more uniform than in here. But in case of smaller molecules, for example, magnesium ion, it forms a double positive charge, and oxide ion, it forms a double negative charge. In here, the ions have charges that are similar, and when they are forming a bond, an ionic bond, the bond will be much more stronger than this bond because of the uniform distribution, and the more positive the ion, the more smaller it gets because the outermost shell electron will be attracted towards the nucleus. Therefore, this bonding between them will be much more stronger, and that in turn allows these substances to have a very high boiling temperature. Since we are discussing magnesium oxide, there is an important property of magnesium oxide that is due to its high boiling temperature. For example, ionic substances that has high boiling temperature often are used as refractories. Refractories are substances with high boiling temperature that are used in different industrial purposes. For example, magnesium, it has a boiling temperature of 2800 degrees Celsius, and thus it is used to line inside of furnaces. So when you are conducting reactions inside that furnace, the furnace needs to be protected. Therefore, the inside of the furnaces are lined with magnesium oxide. So even if the temperature reaches to highs such as 1500 or 2000, the furnace will be protected. And high boiling point ionic substances are also used to make other materials. For example, aluminum oxide. Aluminum oxide has a formula of Al2O3. And aluminum oxide is used to make crucibles and spark plugs. Now you know what crucibles are, right? If you have been inside of a chemistry lab, you will have seen a crucible, which is a form of this round shaped container that we often use to heat substances in. And spark plugs are used in car engines, which is necessary during the starting of the car engine. So guys, as you can see from this table here, there is stark differences between ionic and covalent compound based on these specific points. In case of ionic compounds, as I have been saying over and over throughout this whole lecture, that they have high boiling points, whereas in covalent, unless they are giant or macromolecular substances, their boiling point tends to be low. Electrical conductivity is none in case of covalent. Either macromolecular or simple, it doesn't matter, they do not conduct electricity. But in ionic substances, they conduct only when they are either molten in a liquid or they are dissolved in a liquid. In case of solubility in water, ionic substances are soluble and usually soluble. Not all ionic substances are soluble in water. However, covalent substances are usually insoluble. which is why in case of organic solvents, for example, paraffin, alcohol, etc., these are organic solvents, as in solvents that are made up of C, H, and O. These are known as organic solvents. Any liquid made up of these three elements. In case of organic solvents, ionic substances are insoluble, but covalent substances tend to be soluble because they cannot dissolve in water. This table provides a summarized point of view of this lecture throughout, and I hope that if you find it helpful, you note it down in your copy along with every other diagrams and table that I have provided in this lecture. So this was the completion of part 2 of the chapter Chemical Substances and the Chemical Bond and the Structure of Substances. In this part, we discussed the parameters with which we can discern between the bondings of molecules. We discussed what molecular substances are. We discussed what ionic substances are. We also discussed in detail about model ionic substance sodium chloride, and we learned the kind of bonding and the kind of lattice structure it has. In the next part, the part 3 and the final part, we are going to see metallic bonding and macromolecular substances, and we are going to learn in detail how those bonds make the molecules or the substances the way they behave. So far, I hope that I have been able to help you understand different delicate details of the bondings of chemical substances. And until the next part comes along, have a nice day.